All right, so we are a little bit ahead of Dr. Batari's class. So I can spend probably 10, 15 minutes answering questions about the exam if you guys had any, or we can just jump on forward. For those of you that are on Zoom, please type something into the chat now to let me know that you are here. So anybody have any questions about anything, or you want me to just keep on trucking?
Once I see how poorly I did, I'll have a better idea.
Okay. All right. Well, with that in mind then, today we're going to be talking about transistor models for the forward active region. Yes. Okay, so that is a great question. The project, I'll go through my emails and check everything today. And then send out the list of who's doing what later today. I think I have an hour between 12:30 and 1:30 where I'm not doing anything that I can take care of that. They will be due, let me find my calendar real quick, on January the 20th. So that means you'll have all of next week to work on them, and then the Martin Luther King Jr. Day break, and then the class meeting immediately after that on January the 20th. You should be good. That sound reasonable? All right. So, all righty. So forward active bias mode NPN transistor large signal model. Is everybody saying here? Yep, okay. All right, so in the forward active mode, the base emitter junction, excuse me, is forward biased. So I'll start down here. Here's our base, collector, emitter. Here's our current IC, our current IE, which that E looks too much like a C for my liking. Current IB, here's the voltage VBE, excuse me, and here's the voltage VCE. So our large signal model, since we have a forward bias junction between the base and our emitter terminal, we are going to put a diode where this voltage drop will be VBE, and this will be our base current IB. We also know that the collector current depends only on the base emitter voltage. VBE. So we have a current that depends on a voltage. So that means we are going to put between the collector and the emitter wow, that is not a straight line at all. A dependent current source which is going to give us a value of IC is equal to IS EXP VBE over VT. Just my wife being silly, sorry. So this is our collector current, IC. We know that there is a relationship between the collector current and the base current. So over here, our base current is 1 over beta times IS EXP VBE over VT. And finally, we have our emitter current, where the emitter current is simply the sum of the base current and the collector current. So this is our large signal model, okay? So let's put this guy into action and analyze a few circuits. So let's say that I have the following circuit. I have positive 2 volts applied up here. I'm going to have some resistor RC that is connected between my power supply voltage and the collector terminal. I'm going to take my collector terminal voltage to be the output voltage of this circuit. Then here at the base, I'm going to apply 0.8 volts. So CBE. And let's talk about what we know. So let's say that IS is equal to 5 times 10 to the minus 17 amperes. Beta is equal to 100. And what we want to find, let me draw these in a different color, is IC, IB, IE, and that voltage V out. All right, so I want to talk about something here real quick. We have a large signal model. I'm going to use it, but really the large signal model, we can analyze the circuit as is, knowing what we know about how a BJT transistor works and probably be okay with it. The large signal model, really its best application is informing us of what the small signal model, how it's going to behave later on. But I'm just going to get into the habit of using the large signal model for these biasing circuits anyway. So I just wanted to be clear about that. We could go through this reasonably easy without actually using the large signal model and still figure out what's going on in this particular example. So our large signal model representation of this circuit. Here's my base. I'm assuming that it's operating in the forward active region. And we will need to prove that technically, because there is a possibility it could be acting in saturation mode, depending on what the value of V out is. So let me explain what I mean about that real quick. C IB plus VBE. My vet's office. Hello? Yes. Mm-hmm. Sure. Sounds good. Awesome, thank you. Bye. Sorry about that. Here is my emitter terminal, so I'm starting there. All right, so between the base and emitter terminal, I have a voltage of 0.8 volts applied. So I'm going to throw a voltage source over here with 0.8 volts like so. Between the collector and the emitter terminal, I have a 500 ohm resistor. That's my RC, as well as a 2-volt source. And then this guy is my ground. My output voltage is between my collector and ground. So here's V out. So let's start there. Everybody okay with this redrawing of the large signal model? Where I know that this IC is IS VBE over VT, and IB is 1 over beta IC. All right, so how can we figure out any of those 4 quantities of interest? Let's start there. Anybody got any ideas? Sure.
You just, because E is rounded, that's why you say E between D and meters. The voltage and then C and E is the other stuff.
Yes, that is 100% correct. So in the schematic diagram up here, this is 2 volts with respect to ground where my emitter terminal is grounded. This is 0.8 volts with respect to ground, again with my emitter terminal grounded. So that's why I chose to draw it in this fashion. That's a good question that I guess I should have clarified specifically. The voltages that I've applied in the schematic diagram circuit are with respect to ground. All right. So how can I calculate IC, IB, IE, or V out? Anybody got any thoughts? Yeah, which is no, right? Seems reasonable. All right, so we can say IC is simply IS, which is given to us, times EXP of VBE, which is given to us, divided by our thermal voltage, assuming an operating temperature of 300 Kelvin. This is going to give us 5 times 10 to the minus 17 amps, EXP of 0.8 volts over 26 millivolts. I get 1.153 milliamps. IB is simply 1 over beta IC. So that's just this divided by 100, which is 11.531 microamps, easy enough. And then IE is IB plus IC, which is the same as 1 plus 1 over beta IC, if you want to go that route. And plugging in, we get 1.165 milliamps. So all of our transistor currents here, pretty easy. Once we know IC, we can get all of the other ones extremely easily. How are we going to figure out V out? This is where things might get slightly difficult, and it's very slightly. Yeah, so we know the current flowing through the 500 ohm resistor is exactly equal to IC. So we could do a simple Kirchhoff's voltage law loop around this portion of the circuit. And what we will find is that V out is equal to 2 volts minus 500 ohms times IC, which gives me 1.423 volts. So is this circuit operating in the forward active bias region, the forward active mode? The conditions for that, just to be clear, is that VC is greater than, VB is greater than VE. Also, I think I probably wrote it the other way around. VE is less than VB is less than VC on Wednesday. But is this true? So VE is 0, right? The voltage applied at the emitter terminal is 0. So that seems reasonable. VB is 0.8 volts. So VB is definitely greater than VE. And VC is 1.423 volts. So VC is greater than VB. So we are in the forward active region. So another question that I might ask, and this is one of your homework questions, so that's why I want to talk about it. What's the largest resistor we can put as RC in order to maintain operation in the forward active region? So let's write that down here. What is the continues to operate in the forward active region? All right, so let's talk about a couple of things here real quick. We had our table, right, where the VC is greater than VB is greater than VE. This is forward active. And if VC is less than VB, which is greater than VE, we are operating in saturation. There were 2 other modes as well, but those 2 other modes depended on the PN junction between the base emitter junction being reverse bias, which literally cannot happen here because VB is greater than VE, right? So I'm not going to worry about those 2 guys. So the condition we're looking for then is what resistor value makes VC equal VB. That's the transition point between saturation operation and forward active operation. So knowing that, how would we go about finding our resistor value based on our large signal model? Any thoughts?
Set V out to 0.8.
Okay, so if we set V out to 0.8, that is the exact same thing as setting VC to 0.8, okay? If we change VC here, so if we drop VC by what is roughly 623 millivolts, is that going to change IC at all? No, because IC doesn't depend on VCE, right? So I would argue that the maximum value of the resistor is 2 volts minus VBE divided by IC, which would be 1040.649 ohms, right? In this case, if we use a resistor value that is larger than that, V out or VC will be less than VBE, which means we are in the saturation region, which means we're using the wrong model. Is that clear? Okay. So the model that we've developed here is only applicable in the forward active region. As soon as this guy goes into saturation, we have to develop an entirely new model, which we're going to be working on next week. Any questions on this guy? All right, let's take a stab at another example or two. This circuit, we are given IS is 8 times 10 to the minus 16 amps. Beta is equal to 100. We want to figure out IC. We want to figure out V out. And we want to figure out VBE. So I will clearly define VBE here. All right. This is our circuit. Again, we're going to apply the large signal model. So I'm going to start my base, again, assuming the forward active region, and we'll have to prove it. Between my emitter and ground, I have that 1 kilo ohm resistor. And between the collector and ground over here, I have 2 volts. Oh, and that is wrong. Between the collector and the base, I have a 10 microamp current source directed from the collector to the base. Sorry about that. Does anybody have any problems with this as my large signal equivalent circuit? All right, so we're all in accord that this is the correct large signal equivalent circuit. Excuse me. How could I go about calculating any of those quantities? So you're saying IC is IS EXP VBE over VT, okay? But we don't know what VB is. Right, if we look at our original circuit, VBE is the drop between the base terminal and the emitter terminal. But we can't say that there's no voltage drop over that 10 microamp source. So there's no way for us to say that VB is exactly equal to VC. We have no reason, no logical reason to make that assumption. Okay, so we could get IC from IB. How do we know IB? Exactly, right? We know what IB is because we have a current source driving a particular base current. So IB is equal to 10 microamps, which means IC is equal to beta IB, which is 1 milliamp in this case. And we weren't asked for it, but we could use it, or we will wind up using it anyway. IE is IB plus IC is 1.001. No, that would be 1.01. Come on, pen. Make sure I'm not making it easier. 10 times 10 to the minus 6 plus 1 times 10 to the minus 3. Yeah, 1.01. All right. Sorry about that. So now that we know IC and IE, how do we go about determining either V out or VBE? Sorry, V out, if we look at our original diagram, that is the voltage drop over this guy. So now that we know IE, it's simply 1 kilo ohm times IE is 1.01 volts. How are we going to figure out VBE? Right, now that we know IC, VBE is simply going to be VT natural log of IC over IS. Let's see, so that is 0.724 volts. So now we have the question, is VC greater than VB greater than VE? Or another way to ask it is VCE greater than VBE? Because we should easily be able to see the potential difference between VBE has to be greater than what you would call, I guess, VEE, the voltage explicitly at the, whatchamacallit, emitter terminal, right? Because if we do KVL, VB with respect to ground is VBE plus VE. So inherently, we're still under forward bias conditions here. So is VCE greater than VBE? Well, we know VBE is 0.724 volts. VCE is going to be 2 volts minus 1.01 volts is 0.999 volts. So yes, VCE is greater than VBE. So we're still in the forward active region. Seem okay? Anybody got any questions about this one? All right. Let's do one more and then we shall move along. Similar circuit. But now we're going to tie our base terminal to our collector terminal with a short circuit. And then try to determine the quantities. So this is RE. Let's make it still a 1 kilo ohm resistor. Let's say that IS is 5 times 10 to the minus 16. Beta is equal to 50. And we want to know the same quantities. IC, VBE, and VL. To be clear, here's IC, here's IB, here's IE, V out is the voltage drop over the 1 kilo ohm resistor. All right, so we draw my large signal equivalent circuit. Assuming forward active region. B, C, E, 1 kilo ohm, V out, IB, here's VBE, IS, all right. Who's got any thoughts on this? This one's probably the hardest one in my opinion. Oh, yep, you're absolutely right. There is a short circuit here between the collector and base terminals. Thank you for noticing that. Any thoughts or observations that we can make? I'm sorry, what was that? IB is equal to 1 over beta IC. Okay, we will wind up using that. Okay, yes. So what if we did Kirchhoff's voltage law around the outside? We would have negative V out minus VBE plus 2 volts is equal to 0. So we could say then that VBE is 2 volts minus 1 kiloohm times IE. Anybody have any problem with that? Just use Ohm's law to replace V out with 1K times IE. Well, we know that IE is equal to 1 plus 1 over beta times IC. And on the left-hand side of this guy, we can write VBE in terms of IC. And so we'll have VT natural log of IC over IS. This is very extraordinarily similar to one of those equations we would have gotten analyzing a diode circuit, right? Because that's really what this thing kind of is. So we can use our calculator and solve this guy for IC. So take a minute and do that. Where, to be clear, IS is 0.5 femtoamps and beta is 50. .233 milliamps. All right. So from this, VBE, which is VT natural log IC over IS, I believe we get 0.742 volts. And lastly, we have V out, which is 1 plus 1 over beta IC times 1 kiloohm, and I got 1.258 volts. Is this active, acting in the forward active region? Again, we know VBE or VB is at a higher potential than VE. Kirchhoff's voltage law tells us that trivially. What's the relationship between VC and VB? Yeah, they're the same thing, right? So this circuit is built to operate right on the edge between saturation and the forward active region. So our model is still okay, but it's right on the cusp of being unusable. All right, and it's the way that this guy's designed. This particular configuration where you tie the base of the collector is what's known as a diode connected transistor, which is why we wound up with effectively a diode circuit in order to analyze it. All right. So let's move along to another page. Let's talk about the current voltage characteristics for BJTs then. So I/V curves. This is going to be fairly straightforward. So there's going to be two different characteristic curves. And the first, sorry, my pen thingy. Dang it, we're dropping my stylus. Broke the seal on the tape that I was using to fix this. Oh God, what is happening? Some transistor Q1, and we're going to see what happens when we sweep our base emitter voltage, which we know that our collector current IC here is simply IS EXP VBE over VT. This is getting terrible. Let's take like a 3-minute break while I go retape this so that it stops recording the weird strokes in between letters. Alrighty, hopefully this worked. There's a small broken piece of plastic inside this thing, and I refuse to pay $100 to replace that minuscule piece of broken plastic. So try this again. There we go. All right. So
I have probably a simple question.
sure.
What does that mean?
So I'm changing the voltage. So we're making a plot of IC as we increase VBE from 0 to large values. So that's just a variable voltage source. That's all that's trying to depict there, okay? And it should be fairly obvious that it's going to look something like an exponential curve because there's an exponential relationship between IC and VBE. So when we're holding VC to be a constant value that is greater than whatever VB currently is, so that this thing is always acting in the forward active region, we get a simple exponential relationship extraordinarily similar to what we saw in our diode. Our second characteristic curve will be measured by holding VBE to be constant while we sweep the values of VCE. And here is IC. And so in this case, we are plotting IC versus VCE. This is going to look a little silly, but go ahead and do it. So what we should observe is something like this, which is going to be flat for particular reasons. I'm going to say that this curve is at VBE1, and in some textbooks you see this characteristic equation as plotted versus particular bias current. So VBE1 corresponds to a bias current of IB1. Then we might see something like this. This curve corresponds to VBE2 with a bias current of IB2, and up here will be VBE3 with a bias current of IB3, where VBE3 is greater than VBE2 is greater than VBE1. Notice something kind of important here. We can't start plotting these at exactly VCE is equal to 0, because until VCE is greater than the corresponding VBE, the device is not in the forward active region. So over here, where VCE greater than VBE, this is the forward active region. And between here and here, this is where VCE is less than VBE. And this is a saturation region, which we're not quite ready to talk about just yet, about how the curve behaves there. So in the forward active region, these are our characteristic curves. All right, any questions on this? Fairly straightforward, I think. When we sweep VBE, we get an exponential curve because IC is equal to IS, EXP, VB over VT. And when we sweep VCE, we get constant values because IC is independent of VCE. Seems reasonable. Didn't really learn anything particularly useful from this, but it's going to all come together in the end, I promise. All right. So now let's talk about the concept of transconductance. This is a fairly straightforward topic, but it is actually really, really critical, as we'll see, in using transistors in amplifier circuits, all right? So the transconductance of a circuit is a measure of how efficiently the circuit converts an input voltage into an output current. In a BJT, transconductance GM is defined as the change in the collector current due to a corresponding change in the base emitter junction voltage. So we can do the math here. And see that this is simply IS over VT times the exponential function of VBE over VT, which is then simply IC over VT. So the transconductance here is extraordinarily similar to the inverse of the dynamic resistance that we saw for a simple diode, right? So we're looking at small changes and how things are affected, all right? So this is our transconductance. Graphically, this may be helpful. Let's say that we're so here is IC VBE. So let's call this point right here VBE naught. This point right here, IC naught, this is the operating point or the large signal operating point of the BJT. If we allow a small change in voltage, we should observe a change in current, which is equal to GM times delta VBE. I want to point out something here. It's just a weird little kind of thing here. And so what it is it looks like if you apply a small sinusoidal voltage, you'll get a small sinusoidal output current. But because it's an exponential relationship, not a linear relationship, it's not truly sinusoidal. It's just mathematically very close to that, meaning you'll see that the peak on one side of the average value is larger than the peak on the other side. It doesn't really come into play a whole heck of a lot until you run into situations where your ripple signal winds up changing the operational mode of the amplifier, which is possible, right? So if you have a significant change in VBE that would cause your amplifier to leave the forward active region, you'll start to see lots of distortion, which is something we'll talk about later. So I just want to be clear about that. All right, so our last topic of the day then is going to be our small signal model. And if we have time, we'll work an example that will allow us to show how the transconductance can be used as signal amplification. All right, so small signal model. So we're going to develop our small signal model by showing what a change at the base emitter voltage does to all of the different currents within our device. Technically speaking, we also have to repeat this for a change in the collector emitter voltage, but we know that the collector emitter voltage, IC is independent of the collector emitter voltage. So changing the collector emitter voltage doesn't change IC, which doesn't change IB, which doesn't change IE. So it's really a waste of time. The book does it. I'm not going to bother because the answer to everything is 0. So why bother doing it? All right, so let's say that we have the following circuit. This would be a good spot. And we're going to have VBE plus some small change in VBE. And we're going to measure the effects of our bias current, which should generally be IB plus delta IB. Change in our collector current is going to be IC plus delta IC. And lastly, we're going to have IE plus delta IE. And the change in IE can obviously be encapsulated by simply adding the change in IB plus the change in IC, which we'll see in a little bit. All right, so our large signal model for this guy would be something like this. Delta, that looks like garbage. And our diode. Excuse me. Where? No, goodness, no. This guy is IB plus delta IB. This guy is IC plus delta IC. Well, we're lucky enough, we already know what a small change in IC causes, right? Or actually, we know what the effect of a small change on VBE causes a small change in the collector current because we've already developed that relationship, right? So if we change the base emitter voltage slightly, we get some change in the collector current that is simply the transconductance multiplied by the base emitter voltage. So if we eliminate the DC signals and only concentrate Now on our AC signals, then let's take a look at what happens here, okay? Delta VBE, this guy becomes GM delta VBE. All right, so the change in VBE causes the current delta IC, which is equal to GM multiplied by delta VBE, to flow from the collector to the emitter. That's literally the role of the transconductance. Now I have open circuited the diode. The reason being is that right now we're assuming that voltage is so small that it's not actually enough to forward bias that diode to do any, to let any appreciable amount of current pass through, okay? So this is our starting point. That being, okay, so our next step in this, and I honestly could not tell you why this is done. We are going to replace delta VBE with V pi. That's it. For some reason unknown to me, in every textbook I have found, a small change in VBE is called V pi. So we're just going to change it because that way it'll match the textbook. So we have V pi. And this then becomes GM V pi. Base collector emitter. And again, I don't know why it's called V pi, but it is. So V pi, just to be clear here, is the exact same thing as delta VBE. All right. Now let's talk about something a little bit more pertinent. If a change in VBE causes a change in the collector current, and the collector current is simply a ratioed multiple of the base current, then it stands to reason that changing VBE also changes IB. It has to, right? So delta IB, the change in the base current, is simply delta IC divided by beta. Which is GM delta VBE over beta. And what we have here is a change in the base emitter voltage that is related to the current that flows from the base terminal to the emitter terminal. So we have a proportionality constant between the base emitter voltage and the base emitter current, which we can represent with a resistance because of Ohm's law, right? So I can rearrange this slightly and say that the change in the base emitter voltage divided by the change in the current flowing from the base to the emitter terminal is simply beta over GM, and we'll call this guy R pi. From this, our small signal model, we're effectively done with it until we start talking about second order effects, is this. Here is the base, here is V pi, here's our emitter terminal, GM V pi collector. This is our small signal model. Being able to draw small signal models effectively will make this class much, much easier on you. The large signal analysis is pretty straightforward, even when you have multiple transistors. Small signal analysis is going to tell you how this thing behaves, particularly in amplifier circuits. All right, we got 10 minutes left, so let's look at an example. All right, so let's say that we have the following circuit. 2 volts applied to some resistor, RC, go to value of 100 ohms. We're trying to find the value of the output voltage. And here we're applying some voltage VBE. So let's say for this guy that IS is equal to 3 times 10 to the minus 16 amps. Beta is equal to 100. And our base emitter voltage is 0.8 volts plus 1 cosine omega t millivolts. So a small voltage. We want to know what the output voltage is, what the collector current is, and also what the voltage gain is. And I'm going to define the voltage gain to be the change in little V out divided by the change in little V in. So the AC output voltage divided by the AC input voltage is going to give us our gain. All right. And I'm going to call this guy not and not. So we're just trying to find those values at the DC operating point of this circuit, okay? So our large signal analysis is going to be pretty straightforward. IC not. I'm not going to bother drawing the large signal equivalent circuit here. IC not is equal to IS so the DC portion of our collector current IC is equal to the DC portion of some quantity of DC portion. So let's see, if I put in 3 times 10 to the minus 16 amps, 0.8 volts divided by 26 millivolts, I get 6.919 milliamps. From this, V out naught is 2 volts minus 100 ohms times IC, and I get 1.308 volts. This is the exact same problem we worked at the very beginning of this class with just slightly different numbers. So not spending a whole lot of time going out how we get to from here to there. But VBE is constant, which means if we're looking only at the DC portion, if VBE is constant, IC is constant, which lets us calculate the DC operating point of the system pretty easily. So we're operating at 6.919 milliamps with an output voltage of 1.308 volts. All right, now let's look at the small signal portion of this guy. So for our small signal model, or some of the small signal analysis, it's actually going to be useful to draw the model. So here is R pi, here is V pi, here is GM V pi. I want to point out something here that may seem confusing to you guys, so I'll tell you why. I am connecting that 100 ohm resistor over which I'm trying to find delta V out between the collector and ground. And over here, I have 1 cosine omega t millivolts. Can any of you tell me why that 100 ohm resistor is connected between the collector and ground? Only for the small signal model. So when we apply the small signal model, we zero out all of our DC sources. So if we short out the 2-volt source that's applied up here, that's why we're connecting our resistor between the collector pin and ground. I noticed some people, when they were doing problem 16 or whatever on the test and trying to apply the small signal model, they left the 8-volt DC source in, which completely jacks up your answer because you're no longer applying the small signal model of the diode correctly if you leave the DC sources on. Small signal is for perturbations. DC sources get turned off whenever you're using a small signal model 100% of the time. So I want to make that real clear. Okay. So it should be fairly straightforward that delta V out is going to be equal to negative GM V pi times the resistor value itself, 100 ohms. Does anybody have any questions, comments, or concerns about how I came up with that? So, to be clear, a current of negative GM multiplied by V pi is flowing into the positive polarity terminal, and then good old Ohm's law. Nothing wild or fancy there. So in order to calculate this, we need to know what GM is, and we need to know what V pi is. GM is our DC operating point collector current divided by our thermal voltage. Why we had to bother doing the DC operating point analysis to begin with. So the transconductance of our circuit here depends entirely at the biasing conditions of the DC portion of the circuit, right? So in this case, that is 6.919 milliamps divided by, if we're assuming T is equal to 300K, this gives us 266.106 millisiemens or milliamps per volt. And from this, delta V out is negative 266.106 millisiemens times 1 cosine omega t millivolts times 100 ohms is equal to negative 26.610 cosine omega t millivolts, which means our voltage gain, AV, defined as the change in small signal V out versus the change in the small signal V in, is negative 26.610. So our 1 millivolt signal has a gain of negative 26.61 applied to it. This is an example of what's called a common emitter amplifier. Okay. Could we develop a general gain relationship for this guy? So for instance, what would happen if I increased RC? Would the gain go up or down? This guy right here is RC. All right. So for larger values of RC, does my output voltage get larger or smaller? Larger, right? The gain of this guy is, so let's look at what we have here. We have GM delta V in and RC. Our gain is simply negative GM times RC. We ran out of time here. We could talk about the input resistance, looking in small signal input resistance, small signal output resistance, which are things that'll help us a lot when we start dealing with more amplifier circuits, but I've ran long already, so we'll talk about that stuff later. Okay, so class is over. The roll sheet got passed around or whatever. One thing that I want to point out real quick, is that on courses Moodle page, on the section where it says bonus quiz, there is now a bonus quiz, okay? I did not make it a fully online quiz because I just got annoyed. So instead, it is a 5-question quiz. There are 3 short answer problems and 2 circuit analysis problems. Complete that by Sunday at midnight. It should not take you more than 15 minutes. If it does, you're overthinking it or you're not using Google correctly. The bonus quiz is up. I'm going to be compiling all the project stuff and letting you guys know explicitly who's doing what and all that jazz within the next day. Is there anything else I'm supposed to do for this class that I haven't done other than that? All right. See you guys on Monday, if it's not snowing. Yes. Sure. I have to look at everything and look at the order in which people turn things in. I haven't made the spreadsheet, so I don't know.